Hello everybody and welcome back to Calc 3 Online. So this will seem kind of odd today because we're kind of going back in time and looking at tangent planes again. But with the notion of the gradient, we can actually do it much better this time. So let's just say we have like some level surface, okay, like f of x, y, z equals like k or something. And there's a point on this surface S here. And so C is just some curve through S, all right? And it goes through P, okay? So then this curve could be like a vector valued function, like x of t, y of t, z of t. And if that's the case, then we basically have we can kind of substitute, right? And we could think of this level surface as f of x of t, y of t, z of t equals k. And if we take the derivative of this thing on both sides, right, we would have to use chain rule. And what we would get is the partial of f with respect to x, and then the normal derivative of x with respect to t. So we're taking the derivative, right, on both sides with respect to t. And then we would add partial of f with respect to y, and then normal derivative of y with respect to t, and then partial of f with respect to z, and then normal z derivative with respect to t, and then the derivative of the k part is just 0, right? It's just some constant. So this thing that we have right here, we could interpret it as a dot product. And if you look at it, right, we're basically taking it has the perfect dot product structure of the red thing dotted with the green thing. And the red thing is just your partial derivatives, and that's a gradient, right? And then we're dotting it with the green thing, which is just a normal, r prime of t. So this is basically saying that the gradient of f and the and r prime are perpendicular, right? Because of this 0 right here. So if we think way back, and we had this kind of structure of equation of like a line or plane that extends to like any dimension. But from that, we can kind of, the normal is like the gradient, right? And then we could put in here, right, the gradient and get this as the tangent plane, right? So basically it's saying it's just another way to interpret how to write the equation of a tangent plane. You can literally just take a gradient and pop the gradient evaluated at the point in here. And then you have this like normal, here we're doing r minus a, but here we're kind of switching over to x's and stuff. But we have x minus x naught, y minus y naught, z minus z naught, and the x naught, y naught, z naught are just like the point P right there. So this is just kind of a shortcut if you want to help you basically get tangent planes a lot quicker. So I want to show you basically how this works. So if we wanted to find the equation of the tangent plane at that point to the ellipsoid that's shown right here, we can just basically use this thing, right? So we can find the gradient. The gradient is, and this is a level, surface, so we can do this. And so the gradient is going to be, it'll be like 2x over 4, but then the 2 and the 4 will cancel and you get x over 2. And then you'll get just 2y. And then you'll get 2z over 9. Okay, and we got to evaluate the gradient at the point, -2, 1, -3. And if you do that, you're going to get -1, 2, and -2/3. And then you can just go ahead and plug things in. So we have -1 times x minus, well, plus 2, because minus a -2. And then plus 2, y minus 1, minus 2/3, z plus 3. And then you could do algebra and get 3x minus 6y plus 2z equals -18. But this is perfectly fine to do it this way. I mean, really, if you think about how we did tangent planes before, it's actually basically what we did. I mean, we're getting the same thing. But it's just giving us a shortcut, right? So we can just find the gradient, evaluate the gradient to get that normal vector. Basically, this vector right here is this vector right here. And then we go ahead and just pop things in and simplify it, and you have a tangent plane. So I just wanted to do a few more kind of examples that use this idea a little bit. So this first one says, are there any points on the hyperboloid, x squared minus y squared minus z squared equals 1, where the tangent plane is parallel to the plane z equals x plus y? And so we basically want to know, we need we need the gradient of f, right, to be parallel to the normal for the plane. So the gradient of f is just 2x minus 2y minus 2z. And we basically want to set that equal to some scalar for the normal for the plane, right? Which is just going to be -1, -1, 1. So basically I brought these guys over, right? Just did it that way. Since we're talking about parallel, we could take away all the the 2's here. So really the problem could just become, can x minus y minus z equal, equal c times -1, -1, 1. So that would mean that x needs to equal -c, y needs to equal c, and z needs to equal -c, right? So we want to know, are there points x, y, and z here on this hyperboloid? So we're going to have to go and basically sub these into the hyperboloid. And if we do that, right, we would get -c squared minus c squared minus -c squared, which would, these two will cancel, right? So then the whole thing is minus c squared. Those don't cancel. Sorry, let me go back here. So these two would cancel, right? And then you have minus c squared, and this needs to equal 1, right? And, assuming we're not dealing with imaginary values, which we're kind of assuming here, then no, it does not work. There is no points, right, that basically are on that hyperboloid where the tangent plane is going to be parallel to that plane. All right, so for this one, we got to show that the sum of the x, y, and z intercepts of any tangent plane to this surface is a constant. Okay, so we're going to have to get a tangent plane at an arbitrary point, which I'm just going to use x sub I, y sub I, and z sub I is going to be my arbitrary point. And so we got to go ahead and find the gradient to do the tangent plane. The gradient is just going to be 1 over 2 root x, 1 over 2 root y, 1 over 2 root z, and then the gradient at my x sub I, y sub I, z sub I point, right, would just be 1 over 2 root x sub I, 1 over 2 root y sub I, and 1 over 2 root z sub I, right? And then I can go ahead and pop everything in to the tangent plane. So the tangent plane would be this, all right? And now you can basically, I'm going to do like some kind of clever algebra. So I'm going to actually split these terms and move the x sub I kind of thing over, the y sub I thing over, and the z sub I thing over. And if I do that, I'm going to get that. And this thing, okay, if you multiply like top and bottom by root x sub I, right, then you can kill this square root, and then you'll get one up top, but then you'll have like an x sub I over an x sub I, and those will cancel, right? So actually, this thing, so I'm just going to be lazy and just say copy that down here. And then it's going to equal, I'm also going to cancel all the 2's. So we've got a half and everything, so I can cancel, which is multiplied by 2, right? And so then, if I do this trick where I multiply by, for this last one, it would look like root z sub I over root z sub I. If I do that, right, I'll get, a normal just z sub I, not a root one. And then I have a normal one up top, so then they'll end up canceling, which is nice. And so this right side will just become root x sub I plus root y sub I plus root z sub I, right? And now, this original surface can come in handy because we know that no matter what x, y, and z you plug in, if you add up the square roots of them, respective square roots of them, you get the square root of c. So that's exactly what I have here, and this is kind of like one of the most important punchlines. Then this thing would result to root c, right? So now, what you basically have is, I'm kind of running out of room. So I have x over root xi plus y over root y sub I plus z over root z sub I equals root c. And then if you go ahead and do, like the x-intercept, y-intercept, z-intercept trick where, for the x-intercept, we're basically going to put in y equals 0 and z equals 0, you'll kill these terms. And then the x-intercept would be just, x over root x sub I equals root c. So you can multiply, these two together and get root c x sub I. And then likewise, the y-intercept is just going to be root c y sub I. The z-intercept would be root c z sub I, right? And the question said, show that the sum of those intercepts are going to be a constant, which is pretty clear now because if we go ahead, x sub I, y sub I, and z sub I are just a specific point, right? So if we add, this plus this plus this, it truly is going to be a constant. So that's just kind of a weird example that I think uses some good tangent plane kind of ideas. All right, I got one more. And I just noticed that this thing should actually say something else. So it should say that show that every tangent plane, I want to do tangent planes right now, that is tangent, so it's redundant now. show that every plane that is tangent to the cone passes through the origin. So we're going to go ahead and start by getting the equation of the tangent plane. So I'm going to rewrite this, x squared plus y squared minus z squared equals 0. So then I can go ahead and do the gradient kind of trick that I've been doing. So the gradient of that level, maybe we should do capital F. The gradient of that level surface is going to be 2x, 2y minus 2z. And then I'm just doing it, it's an arbitrary one again. So I'm going to do like an arbitrary xi, yi, zi. And then you would just pop in xi, yi, zi. Okay. And then, from there, we would see that the tangent plane is given by this. So then I'm going to simplify this thing. So I'm basically going to multiply in combined like terms, that kind of thing. And if you do that, you will get, and kind of in the last problem, like I did this trick too, I know that no matter what x and y you square, it equals z squared. So specifically, I can use this over here, right? I can pop in, oh wait, I have a typo. This should be negative because it is, I'm getting a double negative, which is gonna cancel some things out. So this should be negative there. And so what I'm going to do is I'm going to pop in, this equation. And I know that this should then become z sub I, right? Z sub I squared, right? But then I have z sub I squared minus z sub I squared. So actually all of this, if you sub in, let me do that again. If you sub in x sub I squared plus y sub I squared equals z sub I squared, then basically you're going to get this nice thing where this whole right side goes to 0. So the tangent plane is now reducing to x sub I x plus y sub I y minus z sub I z equals 0. And that tangent plane, right, like basically in here, we've got this kind of structure where it's like x minus 0, and then y sub I, y minus 0, minus z sub I, z minus 0. And this, right here tells me that truly, no matter what tangent plane I pick, that will pass through the origin.